So, what I have for my final project is a device that's designed to perform dead reckoning. What that is it is using information from an accelerometer and a gyroscope to perform uh, numerical integration on the device so that you can calculate its current position relative to where it started. Now, it's been a learning experience, and unfortunately, the final device isn't actually very good for um, checking position, but it's pretty good for determining current acceleration and finding the Euler angles. So I'm going to go ahead and take you through the device, and I'll talk more about the problems with it in a little bit. So basically, I've got standard Arduino here that I'm powering with a 9-volt battery. So that I don't have to have it plugged into the computer in order to power it. Then I have this guy here, which is a ProtoShield, onto which I've connected a breakout board for the MPU 6050, which is a accelerometer and gyroscope, all put together in one nifty little package, as well as a Bluetooth package, which is going to allow me to communicate with the computer wirelessly. Again, so I don't have to have it plugged in, which means that I can hold it in this little package and just wave it around, do something with it. Basically, the Arduino program is polling this sensor repeatedly to determine its current acceleration and angular speed. From the angular speed, just by counting angular speed, we're able to determine the Euler angles, which describe the translation or the rotation of the device, which is extremely useful as far as analysis of motion goes, because then, in order to determine the current acceleration relative to its starting frame, we just apply a three-dimensional transformation of the current axes to obtain a new direction for the acceleration vector in its original frame, which is it's nice and easy. But the problem is that we're performing numerical integration, and the Arduino is a little bit slow when it comes to floating point calculations, and it takes a little bit to sample the accelerometer. So while we are oversampling 10 times on the Accel and on the gyroscope, we're still integrating numerically, which means that there are errors, and it turns out that the errors, especially in the Euler angle, really throw things off. So basically what happens is, as I move it around, the Euler angle is actually one of the closest values that it determines, the Euler angles. But after a little bit, it doesn't take very long, the initial frame has rotated because the Euler angles have acquired some error. So once that's happened, we're subtracting out the acceleration of gravity in the initial frame, but once you've rotated the initial frame, gravity is no longer pointing in the same direction, but the program has no way to know about that, and the Arduino can't figure that out, which means that there's this constant small acceleration that slowly is growing and getting larger and larger, and that means that the acceleration is always going to be a little bit off. But it's fairly accurate. Then, when I integrate that to get the velocity, then we're actually increasing the error significantly, because now it's going to be a little bit off in acceleration, but it's going to be that much times the amount of time off in velocity, which is going to get fairly substantial fairly quickly. Then it gets worse, because we integrate position by multiplying velocity by time. So now, as time goes, the error in position increases as that error in acceleration times squared. which means that the error does build up fairly quickly, and it's really not especially possible to determine position with this device because of that error. Velocity is iffy, acceleration is reasonably accurate, and the Euler angles are fairly easy to find. So what I'm going to do now is I'm going to turn the device on, and we're just going to take a look at a capture of it moving, a capture of the serial output of it moving in some frame. So I'm going to walk you through what I have to do. So when it boots up, it has to determine what its initial rotation state is, as well as the initial acceleration. Preferably, your initial rotation state will be 0, and also preferably whatever initial acceleration state you have will be permanently there. For instance, gravity, right? It'll always be there in that frame. And it needs to do those things so that it can zero the accelerometers and the gyroscope. So what happens is in the setup function, when I start it up, it takes about 2 or 3 seconds to go ahead and measure those things and record them, which means that I'm going to place it on the table sitting there, and then when the serial says it's okay, what I'm going to do is I'm going to lift it up, put it above my head, rotate it in a circle, and then put it back down. And then we're going to go look at the serial output from it, as it tells me what the Euler angles, acceleration, velocity, and position it thinks it has are. So let's do this. Okay, so I'm lifting it up above my head, going around in a little circle, and then putting it back down as close as I can to its initial position, and then turning it off. Okay, so let's jump to a screen capture and go look at that serial recording. So this is the serial output from the Arduino, and I do have to apologize because I am voicing this over after having gone through the file and recorded myself looking at it. So it may be a little bit choppy. Up above there, it performs a little diagnostic, lets me know that the device is working correctly. It didn't catch that because I started the capture after the device started up. So it gives you its velocity, its acceleration, velocity, position, and Euler angles in its reference frame. And you'll notice that even though initially it's holding still, that velocity is off just a tad, or the acceleration is off just a tad. It's in units of 8192 per g, which means that we're just smidgen under a meter per second per second. Well, not more than a smidgen. It's significantly under there in the y component, but it fluctuates pretty randomly, so our velocity and position actually end up being relatively okay at this point. But you'll notice that the Euler angle has moved a little bit, so we are going to have this constant buildup of error and acceleration. That's probably because I bumped it or something. It doesn't appear to be building up too quickly, 1/100th of a degree every couple seconds. So yeah, that you can see that the acceleration is actually reasonably accurate. It's fairly close to 0, moving around kind of randomly because of the sensitivity on the device. And then at some point I'm going to pick it up. So you can see scrolling down, eventually the Euler angles begin to shift significantly. That's what we're looking for. So you can see the Euler angles are now starting to significantly shift because I'm picking it up. Most of the acceleration's in the z direction, which makes sense because that's where most of the motion in my circle was. Looks like it's accelerating fairly quickly, and you can see it is recording a velocity and a position, but as we'll see once I return it to its initial state, that position and velocity are not especially accurate. At the end, I put it back down, and the first thing you'll notice is that those Euler angles are fairly far from their initial values of 0. That's because of the numerical integration errors that are building up an Euler angle, and as a result, you'll notice that the acceleration is non-zero, even though it's at rest. This is because the initial frame has shifted by those erroneous Euler angles, which means that it thinks that it thinks that gravity is a force acting on it right now, even though I'm subtracting it out, because it's in a different direction than it expects. So it means that the thing is going largely downward in the z direction. That's in 8192 per meter per second, so a couple meters per second downward. And that's an 8192 per meter, so it's about 10 meters displaced downward, it thinks. Again, this is because of error building up in the Euler angle, and it builds up fairly quickly. So for that reason, the device is not the best for determining its own position. So it's a fairly cool device, even if it doesn't work. I mean, it is capable of giving you instantaneous rotation angle to a reasonable degree of accuracy. It does build up error in time, but more importantly, it can accurately give you the changes in its rotation as well as its acceleration. So the Arduino is only capable of performing really, really basic numerical integration, and even that is slow because it has to do some floating point calculations to do the rotation. So as a result, we're not sampling the accelerometer as quickly as we could be. So if we wanted to improve the accuracy of this dead reckoning device, probably the best thing to do would be to have it spit out time deltas saying, hey, I'm moving at this angular velocity. Oh, now I'm moving at this one. Oh, now I'm moving at this one. As quickly as the Arduino is capable, which ends up being around 400 hertz. And then have something like a computer intercept the Bluetooth or capture the Bluetooth on that, and then use the data that it's being sent to perform more sophisticated numerical integration techniques, as well as just perform the floating point operations more quickly. This is going to give us a more fine-grained sampling of the current acceleration and angular velocity, which is useful because we'll be able to determine velocity and position to much better accuracy. Also, you can use more sophisticated techniques like splining or some form of interpolation to determine more accurately what the acceleration function looks like between samples. And that would greatly improve the accuracy of the simulation. Unfortunately, it's beyond the scope of what I'm going to be able to do for this project, just because of time restraints. So, but that's not to say that a device in this form isn't useful. It could be used as long as it was combined with some sort of absolute positioning system that it could use to remove its errors periodically. Or if it knows that it's restricted to a grid, it might be able to do it. For instance, a Wiimote has an absolute positioning system in the form of 2 infrared LEDs that it uses to periodically determine its position and rotation so that it can correct for errors, but it needs as smooth as possible an input so that it can feel natural. So instead of performing the expensive calculations of where am I relative to those infrared beacons, it just does some simple dead reckoning in order to determine its current motion, and then it updates the error based on the infrared periodically. Additionally, a GPS in a car could use this to determine between times that it pulls GPS, because that's an expensive operation, and it does wear down on the battery life of the device. In between, every 10 seconds, it can sample a GPS, and then during those 10 seconds, it can perform dead reckoning to figure out where it is on the road to a reasonable degree of accuracy, especially because it can remove some of the uncertainty knowing that it's got to be on the road. So that does allow for this kind of device to be useful. But